Okay, it's a great pleasure to have Howard Wiseman back again. He's going to talk to us about quantum enhanced optical phase tracking experiment.
Thanks,
Okay,
Howard. Yeah.
thanks.
So it's nice to be giving another talk in this group. So the work I'm going to talk about here is mainly that in these two papers, one published in 2012 and one in 2013. For anyone who doesn't know, I'm at Griffith University, which is here in the Centre for Quantum Dynamics, and this work is also part of the Centre for Quantum Computation and Communication Technology. So obviously I'm not the sole author on these papers, and so I have one common author on both of these. That's Dominic Berry, who's at Macquarie University. He used to be my PhD student quite a long time ago now. And on the science paper, there's a very large number of authors. Is Akira here? No. So this was an experimental, experimental and theory paper, but primarily experimental, and the experiment was actually performed in the lab of Akira Furusawa at the University of Tokyo, and it involved a lot of people from a lot of different universities. And then the second paper, which I'll talk about, which is a pure theory paper, had myself, Dominic Berry, and Michael Hall, who's a research fellow with me in the Centre for Quantum Dynamics, Griffith. Okay, and a very smart guy. I'm going to begin by giving an outline, but maybe I won't go through it. To say I'll just do a background, then theory, then experiment, and then talk about ultimate quantum limits. But I want to begin, as I said, with his background, which is putting this work in a broader context. So most broadly, it's in the context of measurement and control, which I'm sure most of you know that it's the topic of a book that Jared and I have. And so when you see the words quantum measurement and control and how to put them together, then the obvious thing which probably comes to mind is quantum feedback control. Okay, so that would be taking a measurement result and using that to purposefully change the system evolution in the future on the basis of that result. So indeed, that's so the idea there is to alter the average evolution of the system. And of course, there have been in recent years some very beautiful experiments. There have been experiments in this area going back decades, but recently some particularly beautiful ones. I'm not sure, are any of the authors of this here anymore? In fact, so Maziar was here. Maybe he was the only one. Anyway, these experiments done in the lab of Serge Haroche, controlling with the state of a cavity, microwave cavity. Sure what happened there. Oops, well that's completely. There we go. Okay. I don't know what it's about. Right. Yeah. So I was just flashing this up just to remind you of some of the very nice work done in quantum feedback control. But where this work fits in is a different way of combining quantum measurements and control, and that is this area of which I call adaptive measurement. So it is, the way I define it, it means controlling future measurements on the system on the basis of the results of past measurement, but not with the aim of changing the average system evolution. In fact, that is by simply changing the way that you get the information out of the measurements, you can leave the average system evolution completely unchanged. So the aim of this control is simply to obtain better data, to obtain better information. And as I said, that's a completely different way of useful thing to do involving quantum measurement and control, and something I've done quite a lot of work on. and that's the context in which today's talk falls. So, but again, just to point out that there are actually many applications of this idea. I'll put this up as number 0 because measurement-based quantum computation, which Jared, of course, was one of the first people to introduce, is not sort of self-consciously usually sold as being adaptive measurements, but that's exactly what it is. And so again, so here's a paper from 2006 now on linear optics quantum computation, which showing that that's exactly what it is, that you have measurements on, you start with an entangled state of some photons here, you make measurements on some of them, and on the basis of that, you choose the basis, no pun intended, in which to measure some of the other photons, and as you can see it says here, Pockels-Seltz 1 adapts the measurement basis for this photon according to the results which were obtained here. And so in the end, of course, all you do is absorb all the photons, they all get detected, so the final state of the system is just nothing. So the aim is not here to control the final state of the system, the aim is simply to get the information you want. And in this case, that information is going to be telling you the result of a quantum computation. Okay, so as I said, so that's example 0. Example 1, so this is another experiment, experimental data here. This is for the task of optimal state discrimination. So this was some work which I was involved in the lab of Jeff Pride. And again, in this case, you can show that by using adaptive measurements, you can do better than any non-adaptive measurements. Well, that is restricting to, if you have a series of quantum states, but you're only allowed to measure them one at a time, you can do better by doing that adaptively. Another example, a fairly esoteric one, so this is pure theory, is the example of tracking an open quantum system using a finite state machine. This was some work with Isaac Karasik. And then finally, so all of these papers here, this is just a sample of papers on the problem of phase estimation, okay, because this has been a very important application of the idea of adaptive measurements, because it really is useful there, and I'm not going to talk about these except this last one here is the one that I'll be concentrating on in this talk. Okay, so as I said, there are various types of measurements you can do, phase measurements, there are various scenarios. What I'm going to talk about in this paper is measurements of phase using a local oscillator. So the idea is here that you have a signal which has some phase associated with it, in some sense, and we're trying to estimate that phase, and we can do so by beating that signal, so this is an electromagnetic field, against some other signal with a known phase, which is usually just called the local oscillator. So this is defined to be a known phase, so we're always measuring this phase relative to that phase. There, okay. So if you simply, optics beating them against means combining them on a beam splitter like this and looking at the intensity of the light that comes out. And when you do that, you see that the signal you get depends, of course, on the difference in the phase between these two. Okay? And so if the phase difference is pi on 2, then the signal varies rapidly, relatively, with that phase difference, whereas if the phase difference is 0 or pi or close to that, then the signal you're getting out, which is this current, right, is very insensitive to the phase difference between the signal and the local oscillator. Okay? So this is a technique called homodyne measurements. Okay? So if you knew what the phase you were trying to measure was, if you knew that it was, whatever it was, you can always adjust the local oscillator phase to be working at this point of maximum sensitivity. Yeah, that's fine. But what about if you don't know what this signal coming in, and you think if you're actually trying to measure it, then a priori it doesn't make a lot of sense to say that you know what it is. Of course, you might say that you know it's within some range, but let's consider the case where you have no idea what this coming in is. So then there are other things you could do. So one is sometimes called heterodyne, also dual homodyne. I won't go through the details, it's fairly similar, but basically it's where you scan through all these phase differences here. So although you spend some of the time measuring where it's insensitive, you also spend some of the time measuring where it's sensitive, and on average then you're going to do reasonably well. However, a better idea is to do an adaptive measurement. And so this is, so I should say these pictures I've stolen from very old talks by Hideo Noguchi, because I just can't be bothered generating my own pictures. And so anyway, so this is the idea that we have a signal pulse coming in here. You measure a little bit of that pulse, and in any way you like. It could be quite bad, but you still get some idea about what the phase is from that initial measurement. You then feed that back to change the local oscillator phase to try to work at this point of maximum sensitivity. Okay, so then you measure a bit more and get a bit more information, continually feed that back, change the local oscillator phase, and you keep doing that all the way till the end of the measurement, at which point you've got a lot of information about the phase, and hopefully you've done a good measurement. Okay, so that's what I've done a lot. A third option would be to do an optimal measurement, and you might say, here's a little pretend dialogue. Optimal, that sounds good. What is it? And here the answer is, well, the true answer is we don't actually know in general what the optimal measurement is in a given. Well, in some cases we do, but in other cases we don't. It's actually quite difficult to say. But then you might ask, all right, well, what about in the simplest case where you just have a single pulse coming in with an unknown phase? And I can say, sure, here's the optimal measurement. It's this POVM. And you can say, well, how do I do that in the lab? And I'd say, I haven't a clue. Okay? So this is why, although it's useful to work out how well you can do with an optimal measurement, for example, it doesn't typically turn into something which can be done in the lab, but it sets a baseline so that you know, for example, if you have an adaptive measurement which does as well or pretty much as well as an optimal measurement, then you know that you've done pretty much as well as you can do. Okay, so I'll be showing you results for optimal measurement, as in theoretical results, but yes, all the lab things are going to be based on either this heterodyne technique or this adaptive homodyne or dyne technique.
Sorry, Howard. The signal coming in, that's coherent state.
Not necessarily, no.
Could it be one photon?
Sorry? It could be one photon, yes. And although if it's one photon, you know that the phase you would measure would be completely random, uncorrelated with anything else. So there might not be much point doing that experiment because you wouldn't be able to work out whether it works or not.
Yeah, which field of a single photon is zero, isn't it? And these are first order correlation measurements.
But what you certainly could, and we've done some theory on this, is to consider a single photon which gets split at a beam splitter, so that half of the photon goes into your phase apparatus and the other half goes somewhere else. And then you could certainly look at like how well you can prepare the other half based on making a measurement of the phase on this one.
Because with Matt James and Henry Norton, we've developed the filtering theory for
single photons. Okay. So now I'm going to go through every one of these points. No, I'm not actually. But I want to give you some sort of idea that this is still just looking at a subset of the possible scenarios, i.e., those related to measuring phase with a local oscillator, and there are still many possible things to talk about. But so briefly, within this scheme, within this framework, there are still two main scenarios. So the one corresponds to the one which I showed you the picture of before, where I have a single pulse coming in. So I can think of that as a single mode coming in with some occupation and some characteristic phase. The other case is where I have a continuous beam coming in here. So it's and on which there's not just a phase imprinted, but actually a phase modulation in time being continually imprinted on this beam coming in here. And then, so the aim in this case is just to measure the phase of the signal, whatever that is. Whereas here it's actually to estimate the phase as a function of time. So at every point in time to have an estimate of what the phase modulation, unknown phase modulation on this beam is. Okay, so there are different things to compare. So in the first case, the sensible thing to look at is the mean number of photons in the signal beam, whereas in this other case here, the mean number of photons in the entire beam is infinite because it goes on forever, but we can look at the mean number of photons per coherence time, which I'll call this capital N here. Okay, so then as,
Well, in general, the phase of a state is not even defined? I mean, if I had a squeeze state and then I displace it
No,
in some
no.
different
So
directions, what is it?
yeah, so no. But what we can, it's probably better to talk about that we have a known state preparation.
Yes.
And then an unknown phase parameter is imprinted on it, and we're trying to estimate the classical parameter that's being imprinted on it. Although in the case, that's not always the best way to look at it, because of the case where you have like a single photon or something, or half a single photon. But I mean, in those cases, we can just look at, well, what does the measurement do, rather than how well does it estimate something. So there are different things. But yes, it's probably, for this purpose, easiest to just think about that we're trying to estimate this classical parameter that's being imprinted. Okay. And so so the other thing we do is do it with different types of light. We could do it with coherent states, as John mentioned, but we can also have non-classical states, and squeeze states is an obvious thing. In the continuous case here, then the obvious way to generate a continuous squeeze state is to look at the output of an optical parametric oscillator. And then we can have the different sorts of detection. So I already talked about heterodyne, adaptive, and optimal, and those are all those. So here I've just, as far as I can tell, of all the people who first did the theory for all these different scenarios, what the result is, and then the experiments which have been done. As you see, the experiments are rather lag behind the theory. I guess it's a not surprising situation. These are not easy experiments, especially for non-classical light. Okay, so the colours here are meant to, I'll just point out big things. So the red colours is what I've called the standard quantum limit. So this is the way I've defined it, at least corresponds to using the simpler sort of light, which is coherent light, and the simpler sort of detection, which is heterodyne detection. So that's what I've defined as the standard quantum limit in these two cases. And as you see in this case, you get a scaling of 1 over n. But interesting, in this case, the scaling goes like 1 over n to the half. Okay, so it's actually a different scaling. We'll see where this fits into a broader framework later on. Okay, so that's a red. Is that the orange color is all the scenarios where you do better than the standard quantum limit, but not in the scaling. Okay, so you get a better prefactor, but the scaling is the same. The light blue is where you get a different scaling, but it's not quite as good as the dark blue, which is, although I haven't called it that, is essentially the up. Well, yeah, no, it's not. Shouldn't quite say that. The dark blue is the best that you can do out of all these scenarios. Okay? So again, you see we have a different scaling. Like this goes like n to the minus 2 here, or very close to it, which some people recognize as being the n to the minus 2 as being a Heisenberg limit. And down here, we get a scaling of n to the minus 2/3. Okay? This is with specific assumptions about what this phase modulation is actually, which I'll get to later.
So why is the standard quantum limit n to minus 1 first and then n to minus 1/2?
Because we're talking about a different thing, essentially. Because we're talking about a constant phase, just a single phase, whereas here, a phase which is continually varying. Now, maybe there's a different thing you could measure which would make them look more comparable, but at the end I'll put up a sort of unified theory which has both of these cases as particular limits. So that might help. Yeah. Right, okay, so the experiments, so the experiments have seen, things close to the standard quantum limit and have seen improvements over that. None of the experiments have actually seen differences in scaling because that's extremely difficult to do, but would be very interesting. Okay, so the main point is that to see a better scaling than standard quantum limit, you not only have to have a better state than a coherent state, in other words, you have to go to a squeeze state or something like it, but also you have to go to something better than the standard measurement. So you have to go to an adaptive measurement or an optimal measurement. So that's the main point. Really, the most important point is that that's where it's both necessary to have for this sort of measurement both non-classical states and a better than standard measurement like an adaptive measurement. Okay, so now I'm going to talk some more about this particular case of phase tracking because that relates to that experiment. So, okay, so what are we actually estimating? And the answer is we're estimating a phase which is given by this equation here, where this dV is a Wiener noise process. So It's a low-pass filtered version of Wiener noise. The theory is that I presented was actually for lambda goes to 0, which is just a pure Wiener process. But if when I first suggested this to experimentalists, their thing was, well, no, we can't do that because we don't like things wandering off to infinity in our apparatus. It does bad things. So you have to put something restoring to give this a finite variance essentially. But more or less the only thing that matters is that at short times it looks like a Wiener process. Okay. Is that right? Yeah. That's right.
Low pass filter, I guess.
Yeah. So it's just a low pass filter of the Wiener process. Okay, so that's the thing. So we generate this signal, or the signal is generated electronically and literally imposed using electro-optic modulator on this beam. And the aim is to try to estimate this thing that we do know what it is, but we pretend we don't, and we see how well we can estimate it. All right, what is the thing that this phase modulation is being put on? So it's a squeezed beam. Now, if you're not familiar with quantum optics, this probably won't mean much, but so it's a non-classical type of light. But yes, if you are familiar with quantum optics, it can be characterized by both the amount of anti-squeezing it has and the amount of squeezing, and so it's the fact that this squeezed amount is less than 1, which is why it's not classical, and that's basically the amount of noise. Oh yeah, so here's a picture, right, okay. So the amount of noise in the phase direction of this light is less than the coherent state, and consequently the amount in the amplitude direction is more, so this number is always at least as big as 1 over this number. Okay, so it's squeezed, but it also has a coherent amplitude, because otherwise it would be sitting at the vacuum, and that would be an ambiguity in the phase of pi ambiguity, so it's always displaced. And in fact, there's some subtleties here, but at least I'm going to say that we don't have to worry about the squeezing, the amount of light, so to speak, due to the squeezing, and we're just going to consider the amount of light in the coherent amplitude part of this. And I'll talk about later why we have to drop that assumption at some point, but for the moment I'll do that. Okay, so that's what is going in here to be measured, and then what comes out is the photocurrent. So that's from basically you take the intensity from these two photoreceivers, take the difference, and that's this I of t, and so you work it through, and it actually turns out to begin by this expression here. So it has another noise. So this dW is completely independent of the noise which went into making the phase. This is quantum noise. So that was purely classical noise, right? This is quantum noise coming from, vacuum fluctuations, I suppose it's actually not vacuum fluctuations because we have a squeeze beam here, but it's related to that. So we get a signal that depends on the sign of the difference between the actual phase of this beam, the imposed phase on this beam, minus the local, more or less minus the local oscillator. But the local oscillator, as we'll see later, we're going to use this feedback loop to set the local oscillator equal to the phase estimate of the beam plus pi2, because that's where we want it to be. Okay, so that ends up then just depending on the difference between the true phase and the estimated phase, and it has this noise term which depends in a complicated way on the squeezing. So it has a part which ideally what you'd want is just this part. This is the phase quadrature of the squeezing of the phase quadrature, and ideally you would just have this reduced amount of noise, reduced below 1 because of the squeezing. But because you're not, if I go back to this picture, right, what you're actually measuring, say if the local oscillator is here, it's not going to be perfectly aligned with this phase squeeze beam because you don't actually perfectly know the phase you're measuring. You're just trying to estimate it as you go, and so there's a little bit of a mismatch between the actual phase and the phase your estimated phase, which means that you get a bit of amplitude anti-squeezing. Some of this anti-squeezing contaminates your current, okay, and that's this term here, okay, this first term. So if the whole thing's working well, then this difference between the estimate and the true phase is going to be very small, and so we we make that assumption and expand this current to second order in that thing, and then do another thing, which is to make it everything simple, to approximate this R of t by its average. And so then we end up with this expression here, which is nice because it's now just linear, okay, in the thing we're trying to estimate, and with a constant amount of noise. But this constant noise, you see, still has this contamination from the amplitude quadrature, and the magnitude of that depends on the error in the estimate, this sigma squared, which as yet we don't know, but we're assuming is small. Okay, and as I said, ideally we would just have this contribution, but we actually also have that contribution. Okay, so then how do we get this the estimate which we use in the feedback loop? And the answer is by doing filtering, and that's because we have to, because it's in real time. And it turns out, so for this model here of the current, the optimal filter to estimate this phi is given by this. It's just another low pass filter, so just in a particular limit where again we don't, where it's almost like just Wiener noise, the thing we're trying to estimate, this comes out to be a very nice simple formula, but in general it's more complicated. I just wanted to show you we get something simple in certain limits. Okay, right, so you might think, well then that's also, that's the estimate of the phase that's used in the feedback loop, so therefore that's the estimate of the phase. How well does it do? But no, we don't actually use that as our estimate of the phase, because if we're just trying to estimate what the phase is at every point in time, we're not constrained to doing that in a causal manner. We can just look at all the data we have at the end of the experiment and go back and try to estimate what the phase was. And so that then allows us to do something better than filtering, which is smoothing. And it turns out in this case, it's well known for the linear systems, that the optimal smoothed estimate is simply to take the filtered estimate and smooth it through a backwards in time low pass filter, if that makes sense. So note that we take the smooth estimate at time t involves the filtered estimate at all the future times of that. So first of all, we go through the data causally in time and get our filtered estimate each time. Once we have that at all times, we then go back with that filtered estimate and smooth it from the future to the past. Jason won't like my saying that, but from later times to earlier times, in order to get the smooth estimate. And as I said, this can be shown to be the optimal one under the assumptions we made. Okay, and so in this limit where it's pure Wiener noise, where we always get nice, simple looking results, the smooth estimate, the error in the smooth estimate is half of the error in the filtered estimate, okay, which is a nice simple result. But it's not always that. If you have colored noise that you're trying to estimate, then you get less of an improvement by doing the smoothing, which possibly is intuitive. You can tell me. Okay, so I think that's, to point out what we get. So all of this actually still has an implicit dependence on the error in the filtered estimate, because so R bar depended on the error in the filtered estimate, so therefore gamma here depends on the error in the filtered estimate, and so everything here depends on that thing which we don't know. So the way we solve this is to just self-consistently work out what that error is and substitute it back in, to get a self-consistent solution. And what we find is then this interesting behavior. So that's just essentially what I was saying. But we get because of this contamination term here, we get this interesting behavior that even if everything is sort of ideal, where you're estimating Wiener noise, where you have pure squeezing and where it's working very well, you can actually have too much squeezing, okay, in your system. Squeezing, you can squeeze till it hurts. Which we can, so this is plotting the amount of squeezing. So normally you would think that more squeezing means less noise is always better, okay? And it's true with heterodyne measurements, just as you get more squeezing, you do better and better. But with these adaptive measurements, if you squeeze too much, then you actually start to do worse. Because with these other parameters given, you get, as you decrease this term, although you can, the way it works with the self-consistent solution is that even though this is, you might think this is going to get smaller enough to cancel that term, it doesn't, because as you make this smaller and smaller, this is exponentially getting larger and larger, and eventually you get to a point where this term comes back and hurts you more than any benefit which you're getting from the decrease in this term here. And so, so this is just, so the filtering and the smoothing, that's just a factor of two different, but the important point is this turnaround here, which you see as the squeezing gets too large. Okay, so that was the sort of ideal theory, and now this is the experiment. So I'm going to do the experiment fairly briefly. Yep.
So does it mean that at some point the heterodyne does better than the adaptive?
Yes, I think that would be that. Yeah, that would be the case. Which is obviously telling you then the adaptive is not the optimal measurement to be doing. Yeah.
Well, only if you
It would have to go out to
on this
not here. No, not here. Not shown on this graph. But if you went out to large enough squeezing, then this is going to actually come up and cross over. I believe. Because there's nothing we're not making.
That's not the right thing to compare, I think, because you wouldn't go and sit, at such high squeezing that you
Right,
does
sure.
hurt, and then you have to actually look at.
Yeah, if you think that your aim that you can if you can control the squeezing, you would of course always control the squeezing to sit at the optimal point, and then you can always do better with adaptive. But it is worth making that I haven't made any claim that the adaptive measurement here is the optimal measurement to be doing, and clearly for some states which are being input, it's not the optimal thing to be doing. It just seems like it's a natural. The intuition which I showed, all the way back about wanting to sit at this point of maximum sensitivity, that's the whole motivation for this. But as you can see that actually, it can break down. And there are other subtle things which I could talk about if you ask me afterwards as well, where there are things I'm sweeping under the rug as well. But I'm going to continue to keep them hidden. Okay. So experiment. All right. So as I said, I'm not going to say very much. These are the parameters for anyone who cares. The only thing that of interest is that you can see that these characteristic times or rates rather, are pretty low, right? They're about a kilohertz, which for most optics experiments that's very slow, and that means that they work very hard actually to get everything stable and to get squeezing over a wide bandwidth. That's not the right way. Low frequencies and still working well. Okay, I don't think I need to show anyway. So that's that's more or less. The thing which we had to assume was small in the experiment is always less than 0.2, so that seems like a reasonably good approximation. So this is the usual experiment. People always put this up and say, "Oh, isn't estimation theory wonderful? That we get this that looks like pure noise, and put it through a filter, and miraculously we get something out which actually is sensible." Anyway, so that's what I've got as well. So you can see, I could say why I think it's a little bit misleading to do that, but anyway, so you see that the filtered estimate which comes out of this homodyne current, this is data with squeezing, etc. So it's actually working. You see that it's pretty good at tracking the actual signal, which is up here. And then the smooth estimate, which is taking this, as I said, going backwards and putting it through a filter. So you see, well, one thing to notice, of course, it is smoother, which is, I guess, what you might expect. It's not obvious that this is a better estimate of that, but I think one place where you can tell that it is, if we look at this tick here, that's more or less at the top of a little peak here. Whereas if you look at the filtered estimate, but you can see that the peak here comes slightly after this tick, whereas with the smooth estimate, it's back more or less on top, and that's because the filtered estimate, is always trying to catch up, if you like, with what's going on. It can only use the information it's got up to that point in time, whereas the smooth estimate has the advantage of knowing what happened in the future as well, and so that's a way that even though it's not obvious that this is a better fit, I think the actual fact that the smooth estimate gets the times more accurately, in a sense, is a large part of why that's better. Okay, right, so then these are some results from the experiment. So this is looking at, so what we really wanted to see was that prediction that you can squeeze till it hurts, okay? And so this is the data shown here. So this is the squeezing level down the bottom. The ideal theory, okay, if the squeezing was perfect, then the data would look like this green curve here, okay? And so we would see the effect, but it would only be at these squeezing levels way out here, which is not feasible experimentally. Now, the real squeezing is not quite perfect, which means that the error, so this black line is the coherent state limit, okay? So you might think at 0 squeezing that the data should be on the coherent state limit. But it's slightly above, and that's because we are being quite rigorous here, and any losses, we're not just incorporating that into the definition. We are actually comparing the results we get compared to what you would have in a lossless system with a coherent state. Okay, so it's slightly above because you know we have 10% losses or something like that.
So eta is your detection efficiency?
Yeah, where is eta? No, oh, yeah, so yes, the eta is the, oh, there it is. Okay, thanks, Frank. Okay, so we have 15% losses. Okay, but that's including the detection efficiency and everything else. Yeah, yeah. But that's what, if we had no losses, that would be what we're getting. So we're actually trying to beat that limit. And as you can see, we do pretty easily. Okay, if we ignore the term in our equations, which is this contamination by the amplitude anti-squeezing, then the theory would say that more and more squeezing is always better. But what we see is the theory with that, the theory here too is what actually we expect with the experiment, and you see that we get this prediction that we have a maximum here and that turns around, and that's exactly what we see experimentally. So yeah, so you see that this goes up much faster than it does in the ideal case, and that's because in the real experiment the squeezing is not pure, and that means that the anti-squeezing is even more than it would be for a given level of squeezing, which means that it comes in to hurt you much quicker, and yeah, so it really goes bad. Okay, and then this is just comparing, yeah, the coherent states and the squeeze states to see that. So they're all above the ideal theory. So the ideal lossless theory is this line here for coherent states and this line here for squeeze states. And in both cases it's above, but more above with the squeeze states because they're more sensitive to loss. But nevertheless, there's a quite clear gap between the coherent state and the squeeze state, and they scale with the alpha squared as we expect them to. So it's all very nice fit to the theory. Okay, so that was the theory and for the experiment and the experiment. But what I want to talk about now is the more recent theory which we've done about the ultimate quantum limits to experiments like this. And so I'm going to begin with this very quick review of the quantum Cramér-Rao bound for parameter estimation. Has anybody talked about this so far? Yes, it has been talked about. Sorry?
Several.
Okay, all right. Well, I'll go through it very quickly then. So we have this, right, so you have a generator, which in our case is going to be a phase shift, so G is going to be the photon number. You have this lower bound on the mean square error, which is one of the Fisher information, which for a generated G is given by, for a pure state at least, is given by 4 times the variance in the generator. Okay, and then, so for states which are actually useful for phase estimation, the variance in the number is of order the number squared. And from that, you get then the usual Heisenberg limit, the 1 over n bar squared for phase estimation. Okay. Now, what we're interested in is this continuous phase estimation. So we are interested in a continuous version. So yeah, so what we call it here is, I think this is a standard engineering term for waveform estimation. So you have a continuously varying phase. And so yeah, so actually this was a paper Mankate Sang, myself and Carl Caves had from a few years ago. So yeah, and so it's basically taking the multi-parameter version of this and taking the continuum limit, which as far as we So it involves the, so then the multi-parameter version we have matrices rather than just numbers for the Fisher information. And so FTT prime is to the -1 actually means the matrix inverse of a big matrix, which you might think of like having 2 time indices. And the bound is at when T and T prime are actually the same. So we have this Fisher information matrix, FTT prime, which in this case, importantly, and I guess this is the crucial thing about the continuous limit, is that none of these things are well behaved unless we add some prior information. Okay, if you have a waveform estimation and you don't know something about how it could be varying, then you can't get any bounds at all. So that's a crucial difference from the simple like one parameter phases or the finite number limit before. So in this case, right, so the quantum Fisher information is what you might guess it to be if you're lucky. So it's not just the variance, it's actually like a 2-time correlation function of the symmetrized property of the generator at the 2 times. So here F is actually the photon flux operator rather than the photon number operator, because we're talking about a continuous beam. And the classical part, the classical Fisher information matrix of TT prime is given by this sort of path integral type of expression, which looks very complicated, but actually in the cases we're interested in, this becomes much simpler. But essentially it takes into account the prior information about the phase, which for the experiment which I talked about is essentially the parameters used to define the model of the phase that you're putting on. So that would be so this thing would be a function of kappa lambda in that case. Okay, and the other important thing to note is that here it isn't going to turn out to be important to include the flux from the squeezing. Okay, so the total, we're going to be looking at the total flux as being a coherent part and apart from the fact that you're squeezing. Okay, so how it actually becomes practical is that we look at stationary processes, and for stationary processes, this Fisher information matrix just becomes a function of the time difference. So basically, if you think of it as a big matrix, you're just looking at, here's your big matrix, we're looking at an off-diagonal, essentially defines everything, like an anti-diagonal defines everything, because this matrix is purely a function of the difference between the 2 indices. So so I'm going to use the notation, which is slightly dodgy, of using the same letter to indicate for this function as for this matrix. Okay, so it's whenever now you see it as just a function of the difference, that's shorthand for this thing here. Okay, and so f to the -1 of TT prime. So I think of that as the matrix inverse again, and then it's also going to only depend on the difference TT prime, and so I'm going to write it like that. Okay, and the thing which we need is just f to the -1 is 0, because that's the thing that appears here in the bound. Okay, so because it's a stationary process, what happens is that you do everything in the frequency domain. You take Fourier transforms of everything, and it all becomes much simpler. Okay, so in particular, it turns out that the thing I want in the Fourier transform of it is just an expression like this, and moreover this classical, so the Fourier do all that stuff, take this incredibly complicated looking expression, and this thing is just the spectrum of the phase fluctuations. So it's actually all really relatively straightforward. That's all that this classical Fisher information in the Fourier transform picture is. So for example, for Wiener noise, that just looks something like that.
So somehow you need that is Gaussian, right?
So that's assuming, absolutely, that's assuming that they're Gaussian fluctuations. So I'll state the assumptions more rigorously later. Yeah, you're right. This thing is more complicated, but so we can't actually work this out exactly, but we can bound it, which is all that we want. So essentially we work out this Fourier transform, then we Fourier transform again to get the thing that we want. Okay, and so also we're going to make it simple by working in an asymptotic regime, so in other words, a limit of large n. Okay, so in that limit, And this quantum Fisher information looks like this. So this is the coherent state part, and then this is the more complicated part, which depends on, now what's crucial here is the bandwidth of the squeezing, which is appearing in these things, so it's all, yeah, it's complicated, there are relations between those. Okay, in the coherent state case, where there's no squeezing, so these two terms disappear, you can see that we'd expect it to be quite simple because they just have a delta function here, and actually is very simple, and you work it through and you get this expression here. Okay, so this was the n to the minus a half, which I said, and which the experiment saw as well, this scaling n to the minus a half. As I said, yeah, and so that's the lower bound, and essentially we can get, well, we showed still in the experiment that we got very close to that, in fact. Now, for the ultimate limit, with this squeeze input, it turns out that you actually want to work in the regime where the flux due to the squeezing is much bigger than the flux due to the coherent state, and if you work it all through and make approximations, what we get is this answer here, which is that the best lower bound we can get is this scaling of minus 2/3. And moreover, what we've shown numerically, so this was some work which Dominic did largely, which was published last year, is that using an adaptive scheme, a quite complicated adaptive scheme, and doing numerical simulations, that we get something very close to this n to the minus 2/3 scaling here. So slow here stands for sub-logarithmically with this parameter. Or it could stand for a slowly varying function, whichever you prefer. But it is actually sub-logarithmically, so it is very slow. Okay, and so yeah, so you have to choose the amount of squeezing and the bandwidth of the squeezing optimally. You have to choose all these things optimally to achieve this, but that's what we showed that you could actually do. Okay, so that was related to the particular experiment, but what we wanted to do was something more general, which we called the Stochastic Heisenberg Limit. This idea that generalizing the Heisenberg limit to the case of a stochastically varying noise phase rather than just a single phase. And so these are the assumptions we made. So first, that the statistics of the field quadratures, so that's these things which are squeezed or anti-squeezed, are stationary and Gaussian and time symmetric, which is another one. And then the second one, that the phase fluctuations are stationary and Gaussian with the spectrum given by this.
This time symmetric, the correlation functions don't depend on the sign of TNT prime, or what is it?
Yes, so I think the back, so that this is the same if I swap T and T prime. Yeah. And it's stationary as well. Okay, so the assumption we make on the phase fluctuations, now we're going to generalize from saying that it's Wiener noise to just saying that at high frequencies it obeys some power law. Okay, that's what we're going to say. So P is the power in the power law, and it has to be between 1 and infinity. And so you say, well, what does this P mean? Well, P going to infinity is essentially like saying that the phase fluctuations vanish at high frequencies. So you can think of that as being that the phase is sort of effectively constant for some time and then switches to some other value and then switches back. But there are no rapid fluctuations in the phase. Okay, it's very slowly varying on. Yeah, it will vary, but it will be, that variation is going to be slow. It's a bit hard to interpret this, but that's the best I can do. Okay, P equals 2 is the model we already met. That model is Wiener noise, or indeed the low pass version of that, which is Ornstein-Uhlenbeck noise. Because it models this as well, because all we're doing is making a statement about the high frequency fluctuations. So the low pass filter doesn't make any difference to the assumption which we're making here, and all of that is because we're interested in this asymptotic limit. And the asymptotic limit to how well we can do is all going to be determined by the high frequency parts of the noise, short times. It's basically how well we can track on short times that determines the ultimate performance of this. Because on long times, you're always going to be able to track reasonably Okay, and then finally the limit p going to 1, that's the case where it's actually divergent, so the fluctuations are just too violent for doing point estimation at all. You can't get anything sensible out of this. But anyway, between 1 and infinity, we can get a sensible result. And what we find is this result here. Okay, so this is the, it scales at least as well, at least like this. Could be so it's a lower bound on the scaling of the mean square error. And yeah, so we get this interesting, the 1 on the flux raised to the 2 to the p minus 1 over p plus 1, which is probably not something you could just guess, but that's the way it works. Whereas if I put in a coherent state, we get so this is what we call the stochastic Heisenberg limit. The stochastic coherent state limit is when you have no squeezing, and there you get it to a different scaling here. Okay. So in the limit p goes to infinity, which is like this very slowly varying case, as I said, what you find is that the stochastic Heisenberg limit just becomes what you'd expect the normal Heisenberg limit to be, 1 on n squared, and the coherent state limit goes like 1 on n. So we recover the ordinary Heisenberg limit for the case of very slowly varying phases, which is a nice thing to be able to do. For p equals 2, we get back those scalings which I told you before, and as I said, in the limit p goes to 1, both of these diverge. You can't actually do point estimation in that way. Okay, so, yeah, I think this is fairly good time. Maybe I'll skip over most of these conclusions though. So we've done the experiment, we've seen what we predicted, which is for this particular adaptive scheme that you can have too much squeezing, but then we've also derived this very general stochastic Heisenberg limit in terms of the total photon flux. And what we think is that we've done simulations in a particular case which suggests we can attain that. This is the future. One thing you could ask about is experimentally, could we actually see some of these things like the difference in scaling? We've thought about that, but it is really very challenging because you would need very high efficiencies, squeezing which is very deep, in other words, a large amount of squeezing, but at the same time very pure, and that's also extremely challenging. And you would need to be able to optimize the bandwidth, the frequency of the squeezing as well as the amount of squeezing, and to stay at the optimal point, which is an awful lot of engineering. So hopefully, it might get done sometime, but it's very challenging. In terms of theory, so when I last gave this talk roughly a year ago, these were the open theory questions which I had there. So can we show that we can achieve the stochastic Heisenberg limit in all cases, and can we dispense with some of the assumptions that we had to make in order to derive it, in particular that you have time-symmetric Gaussian statistics. What else was there? Stationary, time-symmetric Gaussian statistics for the field quadratures. And so I'm going to flash up some still being written work where essentially we do those things which I set out in that in the future then. So this is almost not the future, but still. I got permission from my co-authors here to put this up. As I said, this is still in preparation. So it's the same authors as before, plus Mankai Tsang. And this was building on some work which he did of getting bounds not from the Crame-Rao formalism, but using the Zib-Zakai formalism, which I had no familiarity at all with before seeing his paper. And it turns out that this is actually even more powerful and does allow us to get bounds with fewer assumptions and through an awful lot of hard maths, which I didn't contribute much to. My co-authors were able to show that indeed you can get exactly this scaling with very minimal assumptions. So we do still have to make the assumptions of Gaussian stationary statistics and this parallel spectra for the phase, but we essentially don't have to make any assumptions about the light which is going in. Okay, we don't have to assume that it comes from a squeezer or anything like that. We essentially don't have to say anything about that, and nevertheless we can get this bound in terms of this mean photon flux. So it doesn't. I think it probably doesn't even have to be stationary. So yeah, so essentially this is true. The bound we previously had is true for arbitrary quantum states. And as it says here, we provide strong arguments, and I think as the paper is progressing, those are becoming more and more rigorous, that we can actually also achieve these bounds. So yeah, so still, yes, more of the sophisticated techniques from engineering estimation and control theory are coming into quantum measurement theory now, and enabling us to prove some very powerful things. So I think that's very good. Okay, thank you.
Alicia.
Well, this may already be covered by this, but I daydreamed for like 30-40 seconds and I lost. So, since your optimal strategy depends a lot on the squeezing, wouldn't it be worth to include, like say, which you may not know, wouldn't it be worth to include squeezing estimation in the the original treatment you did? How involved would that be? That you estimate both squeezing and the phase.
We could do. Yeah, we could do that, but I guess we're just assuming that you know what the squeezing is.
Yeah, I know. I mean, how involved would that be? It becomes.
Well, I think it would become. I mean, I'm not sure exactly how you model, but if you're thinking of it in terms of, the thing about the phase estimation is that this is a task which never ends. It goes on, and you never get to a point where you say, I know the phase, because you're just always having around the phase.
Yeah.
Whereas, if it's saying, well, I have some set up with some, squeezing parameters here, which I don't know, after a certain amount of time, well, you're going to know them. So it's not really a stationary problem in the same way that estimating the phase is. If that makes sense. So yeah, it's not that
you
it's
improve your tracking on the go. I mean, if you filter and not smooth.
Yeah, but again, at some point you would know the parameters, presumably, and then afterwards it would be. I mean, yeah, so in terms of a transient, if you had to do that, but I mean, the thing is that, actually in the experiments is that they would have other ways of estimating those things offline. And,
Can you go over what your parameter P means again? Because towards the end, because it turned out a little bit more fundamental, and so I kind of missed what does it really mean?
Yeah, well, it's saying something about how quickly the phase spectrum falls off with frequency. Okay, so when as P goes to infinity, then this right, when P goes to infinity, that's effectively saying that the phase spectrum looks, well, I mean, we don't really say anything about what it looks like at small frequency, but essentially it's saying that it goes to zero outside some band. So it's like you have band limited noise, and maybe some engineer could give a picture of what band limited noise looks like. I don't have a great intuition about it. Whereas, yeah, as I said, Wiener noise is where it's rolling off as 1 over omega squared, and if it rolls off as slowly as 1 over omega, then that's actually because then you actually have an infinite amount of noise under your spectrum because 1 over omega doesn't converge, and so it's not surprising then that in some sense you have infinite fluctuation.
That P equals 1.
That's the P equals as P goes to 1. So I don't know whether anybody else can give any more intuition about what a spectrum like this means, but that's.
I've got one more question.
I mean, this kind of scalings, like you have, I mean, I'm not familiar with this setting.
Yeah, like these.
These kind of scalings are kind of also observed in theory of atomic clocks.
Sorry, there what?
In theory of atomic clocks, this kind of scalings, it should be somehow, I guess it should be somehow related.
Yeah, you might. Yeah, I guess you think if they're limited by noise with some power spectrum.
I mean, if you see the limitation from the local oscillator noise,
yeah,
then you have similar scalings.
Okay. Okay, maybe we should talk about that because I know that's what they're limited to is the phase fluctuations in a local oscillator.
Yes, and then somehow depending on the whether it is 1 over f noise or 1 over f to the p noise, you'll see such similar scalings.
Okay,
So it
okay.
should be
I mean,
somehow
presumably
related.
they don't have non-classical states, so it probably looks like this. Presumably.
No, of course, not in experiment, but in
Yeah.
theory somehow.
Oh, in the
people-
theory.
People,
Okay,
play
okay.
this.
Yeah, okay, so I'd be very, yeah, if you have the, like, can show me the references, I'd be very interested in seeing. Thanks.
One of the things I find really surprising about the previous slide was just this noise scaling thing, is that it's on 5. Because usually when we want to make physical limits, we actually work with the quadratures themselves.
Okay, but this is a classical phase, if you like. It's a phase noise that's so don't think of phi as being a quantum operator. Yeah, so this has nothing. Yeah, so you can write down a quantum phase operator if you like, but this is not what I mean. That's not what we mean by this, because this is talking about the statistics of a classical parameter, which you know, like, I mean, in a real experiment, it might be that you're trying to estimate you're bouncing your thing off a mirror which is moving, and you're trying to estimate where that mirror is, and so then that phi would then be exactly the position of the
So
mirror.
let me then ask the question, which is, if I took white noise in the quadratures,
Well, there white
what would I
noise
get
in
from
the
phase?
well, I mean, in the coherent state case, you do have white noise in the quadratures.
But I don't have it in 5.
But you don't have the, well, white noise would, I don't think, no, white noise in, well, I mean, integrated white noise in phi is just the Wiener process, is just this p equals 2 case.
Yeah.
Right. But I'm not sure if that's what you're asking or not.
I think I'm suggesting that this constraint here may be actually more physical, natural, than it looks at first glance. Once you realize
Okay.
that it's on phase rather than
Right,
on
right, yeah. No, I think, yeah, we were motivated by the idea that typically you do have power laws for high frequency fluctuations, for some noisy parameter that we're trying to. Yeah,
You would have all some of them, right? It would be, like mass, right? It would not be one parameter. You would have all some of different scalings in the real noise.
Right. So the ultimate limit is then going to be set by whatever is dominant at high frequencies. And maybe you never, maybe there are always new things coming in. I don't know. Maybe you don't always have a well-defined peak, but yeah, under the assumption that you do, then we can get it.
I think just one last question, Jason.
I thought I should, as an engineer, I should ask you about applications. I mean, you mentioned the fact that the phase that you're trying to recover is a classical signal.
Yeah.
Typically, in communications, that would be some sort of phase shift keying protocol for communicating digital information.
Yeah.
If you can naively might say, well, if I can estimate the phase better, I can have a denser phase shift keying space.
Right.
But here, because you're restricting it to Gaussian type signals and Gaussian
Yeah. It
Station
doesn't really
process.
fit that.
it won't work. Is that because essentially you're far away from the limit in terms of the Nyquist limit? So if you were thinking about,
Yeah.
if you were saying, well, I'm communicating information at a certain rate,
Yeah.
because you're restricting it to sort of stationary Gaussian type signals, then you're actually quite far away.
I
from
think,
that.
I think the answer would be yes. And I guess because we're treating this as an estimation problem, not a discrimination problem. I guess communication is really about discriminating between signals, whereas we're just talking about. So no. I mean, so the application would not be, would not be for that scenario, but more like you have some physical process that you are trying to keep track of.
Yeah, okay. But say you have a situation where your phase signal, classical signal, is say some sort of telegraph noise process.
Yeah.
That would be the simplest kind of phase shift key.
Yeah.
Could you go through the same process? Do you think there would be any advantages of a quantity phase estimation in that sort of scenario? I think that would be quite an interesting one to do.
Yeah, I see. Yeah. I mean, it would be. Yeah, a lot of the techniques only work when you have Gaussian noise. So if you have telegraph noise, then that will break those
assumption, it might be other assumptions.
No, absolutely, yeah. I mean, like there should be, you think that there should be an advantage in using quantum states.
There's always an advantage.
Yes, that's right. It can't do worse, so therefore there's always an advantage.
Okay, no further questions, let's thank God again.